the third paper in this session is called CloudVisor Retrofitting Protection of Virtual Machines in Multi-tenant Clouds with Nested Virtualization from Fudan University in China, and the paper is presented by Fengxi Chang.
Morning, everyone. And thanks for the introduction. And I'm going to introduce a system called CloudVisor that protects the virtual machine from in multi-tenant cloud. Okay, multi-tenant clouds, also known as public cloud, is already widely available now, such as Amazon EC2, Rackspace, Go, Grid. If they provide a computation infrastructure as a service, that means computation resources are rented as virtual machines. And to save the cost, virtual machines from different users may run side by side on the same platform. Here is a typical software stack in a multi-tenant cloud that usually composed of a hypervisor and a control virtual machine, and user can rent virtual machines running on the hypervisor, and if he rent more or less computation resource, he can rent more a different number of virtual machines. A multi-tenant cloud has lots of merits. However, the question here is, can we simply trust the multi-tenant cloud or public cloud? Lots of evidence have suggested that the answer is probably not. And here I will list two reasons. The first is that there are curious or malicious administrators. As the hypervisor is the most privileged software on the platform, it can access all the resources, including the user what's inside the user virtual machine. So if the problem goes here, if the administrator or the operator in the cloud turns malicious, he has already had the control of the control virtual machine and the hypervisor. And so it's very easy for him to intrude into the virtual machine and get any sensitive user data or tamper with the user data. As quoted here by Gartner 2008, the most concerned security issue in public cloud is invisible access to unencrypted data in its facility. And this threat is very real. I listed the newspaper here that says Google has recently fired an employee for spying on kids, and he has picked into lots of private data, for example, emails, chats, for several months before it is discovered. Another reason why we cannot trust the public cloud is its extremely large trusted computing base. The trusted computing base usually includes both the hypervisor and the control virtual machine. In the case of Zen system, and the DOM0 kernel and tools. And we can see from here that the problem is increasing. From Zen 2.0, the trusted computing base, or TCB, counts about 5 million line of code. And when the Zen is evolved into Zen 4.0, the TCB size increases to about 9 million lines of code. And this problem has already been explicitly stated in a previous talk, I guess. So for a monolithic virtualization stack, the problem is 1 point of penetration leads to 4 compromise. So that's 2 problems. And these problems lead to the result that currently we have not seen any cloud vendors who can claim 100% secure of user data. For example, in the end user agreement from Amazon, they stated that we would strive to keep data secure, but cannot guarantee we were successful at doing so. And the same goes for Microsoft Windows Azure platform that states that user is suggested to using particular methods like encryption and decryption for the particularly sensitive data of his own, by his own. And we can see that encryption of sensitive data is one way to go. Encryption is good for static data storage. That means data never get decrypted in the cloud. And cloud is just used as an online storage space. However, as for the computation cloud, data are involved in the computation, such as web service, and data should be decrypted during the computation. That means, in that case, encryption alone is not enough. And to be noted that computation cloud is a more widely desired cloud form. So the goal of CloudVisor is to defend against curious or malicious cloud operators to ensure the privacy and the integrity of user virtual machine. And the second goal is CloudVisor would like to be transparent to existing cloud infrastructure. That means little or no modification to virtualization stack, including the operating system and the hypervisors. And the third goal is, you would like to achieve it with the minimum traffic computing base, the code size, so that the CloudVisor itself can be easily verified for correctness. And non-goal for CloudVisor is DOS attacks, and also do not defend against side channel attacks or any semantic attacks to the virtual machine services from network. The key observation here is we can live with a compromised virtualization stack. And the key idea is we can separate security protection from the mechanism of VM hosting. That CloudVisor, as another layer of indirection, is solely in charge of security protection of virtual machines, and it interposes between virtual machine and hypervisor. While traditional hypervisor, most likely unmodified, is in charge of VM virtual machine multiplexing and management. And this separation results in minimized trust computing base of CloudVisor, and both hypervisor and CloudVisor can be separately designed and evolved. Okay, here is an overview of how users can leverage the CloudVisor system. And firstly, as usual, there are the usual virtualization stack on the platform of public cloud, including hypervisor and the control virtual machine. But there is also a hardware security chip installed on the platform. And the security chip would first launch CloudVisor before the hypervisor. And the CloudVisor is running underneath the hypervisor. And after this, the system is booted. A remote cloud user can challenge the security chip to get an evidence of an intact version of CloudVisor. This is done by the security chip that signs an unforgeable attestation and send it to the end user. And the user can be sure, using that attestation, that a correct version of CloudVisor is running on the remote platform. After making sure he can encrypt the virtual machine image and upload it to the platform. And then CloudVisor is able to run the encrypted virtual machine upon the hypervisor. Here is how the approaches of used by CloudVisor to protect virtual machine computing resources. At the bootstrap time, trusted computing technology is used to make sure CloudVisor is safe itself. And for memory spaces used by the virtual machine, CloudVisor interposes address translation, and it allows illegal mappings to the virtual machine memory by the hypervisor or anybody else. As for the I/O data, as we previously have seen that beforehand, the user has already encrypted the whole virtual machine image. And at the runtime, the encrypted data is transparently decrypted when it is loaded into the memory of virtual machines. And as for CPU register states, CloudVisor also interposes the control switch between hypervisor and the virtual machine and hides the CPU register states from the hypervisor. And this is all discussed in the paper, not included in this talk. And the first step is bootstrapping the trust. We leverage two basic trust computing technology, naming authenticate boot and remote attestation. So at system boot time, BIOS would first load grub, and grub would load the CloudVisor. But in the trust computing technology, before the BIOS loads grub, it will first measure the binary of the grub. And the measure is like a hashing algorithm, and the hash value is then stored in the hardware security chip. In this case, it's called a TPM chip. And in turn, before grub loads CloudVisor, it will also measure the binary of CloudVisor, and the measurement result is stored in a chip. And the chip is not compromisable by software. After the system is booted, a remote user can challenge the TPM chip to get the previously stored hashing value. And these values are signed by the TPM chip, and it could not be forged. Using these signed hashing value, the remote user can be sure what exactly binary is running on that platform. So, after bootstrapping of the trust, CloudVisor interposes all the architectural events by nested virtualization. CloudVisor is based on standard hardware support of virtualization, such as VTX and VTD, but it's tailored to only host one hypervisor. And the hypervisor runs in unprivileged mode, while the CloudVisor runs in the most privileged mode. Here is the tailored one-on-one nested virtualization. That means CloudVisor could host one virtualized environment. And in that environment, one hypervisor can be run. But upon that hypervisor, multiple virtual machines can be hosted. And here is the preliminary of VTX technology. In addition to traditional CPU privilege level, in the hardware virtualization support, like VTX, there are another new privilege mode called host mode introduced. And both in the host mode and the guest mode, there are all the traditional CPU privilege levels. And hypervisor is designed to run in the host mode, while user virtual machines are designed to run in the guest mode. All the privileged instructions running in the guest mode will cause a tramp into the host mode. The tramp is called VM exit. And after the hypervisor has handled the exception or the tramp, it will resume the execution of the virtual machine using VM entry instruction. And in the scenario of CloudVisor, the hypervisor is pushed to the guest mode, and the hypervisor does not know about that. And the CloudVisor runs in the host mode. And if the virtual machine is executing some privileged instructions, it will jump into the CloudVisor, and the CloudVisor would simply pass the event to the hypervisor. After the hypervisor has handled the event, it will exit to the CloudVisor, and the CloudVisor would in turn resume the virtual machine for the hypervisor. So, in this position, the CloudVisor is in the most privileged execution level, and it can interpose on any architectural events. This is the base of how the rest of the protection mechanism is done. And let's see how memory isolation is done. The goal of memory isolation is to forbid hypervisor access to the virtual machine memory. And the rules here is when a page is assigned to a virtual machine, CloudVisor would change the ownership of the page to that virtual machine. And the memory page is only accessible to its owner. And with the hardware assist of memory virtualization, like extended page table, we can see that traditionally memory access involves an address translation that goes from virtual address to physical address. However, in the virtualization, this translation needs two translations. That goes from guest address to host address, guest virtual address to guest physical address, using the page table in the virtual machine. And then the guest physical address is in turn translated into host virtual address using the extended page table. Extended page table is very similar to the page table, but it is used to do another layer of the address translation. The virtual machine is aware of the page table only, while the hypervisor or the CloudVisor is aware of the extended page table. So here we will transparently control the address translations, and we only control the translation in the extended page table. So for each virtual machine, there will be an extended page table maintained by the hypervisor. However, in the scenario of CloudVisor, the extended page table maintained by hypervisor is set to be read-only. So any updates in the extended page table would be validated by the CloudVisor. And there is an extended page table for the hypervisor that he does not know. And it's maintained by CloudVisor. It's invisible to the hypervisor. And in that extended page table, there is no mapping to the memory of virtual machines. And this guarantees that a page is either mapped by a hypervisor or by a virtual machine, but not both. And the CloudVisor tracks the ownership of every page. Another major resource to protection is I/O data. And CloudVisor intercepts and passes all the disk I/O requests from the virtual machine, including programmed I/O and the DMA, and transparently encrypted and decrypted data transferred into or out of the virtual machine. And also, hashes are calculated and compared to verify the integrity of the data. However, this detail will not be discussed here. And as for network I/O, it's merely transferred by the CloudVisor, but it's not encrypted or decrypted at all. Here's an example shows how a disk read is done. Firstly, the disk read, the request issued, and the hypervisor would load the data from the disk. However, the data is in an encrypted form. And then the hypervisor will try to copy the data to the memory of virtual machines. However, he does not have the memory mapping in the extended page table, so that would cause a tramp into the CloudVisor. But to handle that exception, CloudVisor would decrypt the data and call-base it to the memory of the virtual machine I/O buffer. And CloudVisor works with traditional VM save, restore, migration operations. For VM save, it's transparently encrypted and hashed. And for VM restore, it's transparently decrypted and verified. As for the migration, some modifications is needed that the source and the destination migration would need a migration entity would need to exchange keys before the migration. And as for the transparent memory sharing, it's not currently supported. And we have implemented CloudVisor based on Zen hypervisor, and it could run modified Windows and Linux virtual machines, and with a very small patch in Zen to reduce the VM exits, and it's only optional, and for Intel platform, and CloudVisor supports SMP system and can run multiple virtual machines, and it's only implemented with about 5,000 lines of code. And to evaluate the performance of the CloudVisor, we'd like to answer 3 questions. How much overhead does the CloudVisor incur? And the source of the overhead, and is CloudVisor scale? We run the test environment on Dell server, and the software configuration is Zen 4.0. And for the unit processor benchmarks, the average overhead is around 2.7%, comparing CloudVisor to a modified Zen hypervisor. And we stress the system with IO-intensive workloads like dbench, and we can see by increasing the number of clients from 1 to 32, the performance of slowdown increases to 54%. And to break down the performance overhead, we can see that I/O, encryption, decryption, and copying is the major overhead. And to evaluate if CloudVisor is scalable, we use Kbench to running in the configuration of multi-cores, and we can see that from half cores to 8 cores, and CloudVisor incurs relatively steady performance slowdown, all are below 10%. And when running with multiple virtual machines, the overhead is at most 60.8%. We have a lot of related work, and the conclusion here, and to take away points, hypervisor can host virtual machines without knowing what's inside. That means hypervisor can provide services without being trusted. The second point is we can do that with a very small code base, around 5 kilolines of code. And our future would be to incorporate CloudVisor into hardware and to reduce the overhead and the complexity. Thanks.
Hi, Olna Gmonbanilde from the Technion. What are your plans regarding memory over commitment? Because it seems there is a problem with deduplication and guest swapping.
Your question is the data swapping.
Guest swapping, the host swaps the guest out of memory, but he can't touch the memory pages.
Yeah. Your question is what happens if the memory is swapped to disk, right? Yeah. Okay. In that operation, the hypervisor would actually access to the memory of the virtual machine. However, this access could not be identified by the CloudVisor. So CloudVisor would assume the memory access is not legal. Then he would encrypt the memory content before giving the memory mapping to the hypervisor. So after when the hypervisor is able to read that memory, all the contents will be in encrypted form. So when this data is swapped back into the memory, and the CloudVisor would reversely decrypt all the data.
Okay, and thank you. And the deduplication?
What did to?
That the hypervisor identifies the two pages are the same and holds only one copy. Can it still be done?
Oh, I cannot hear you clearly.
Deduplication. The hypervisor normally removes duplicate copies of the same page. Can that be done?
Oh, yeah, duplication. That will be a problem here. And we currently do not support duplication. And maybe that could be a future work.
Hi.
Yeah.
I think CloudVisor is a very nice system. Congratulations. My question is about I/O sort of security and virtualization. And you talked about how you protect disk, right? And you talk about networking, and you said, you pawn that to the OS, maybe use SSL. But how about other devices like, you want to run a legacy operating system in this VM that needs a real-time clock. That real-time clock is virtualized by a virtualization stack that can be compromised or can do whatever you want with it. How do you know that you're not going to expose the integrity of that legacy OS just by playing with the RTC?
I guess your question is how to handle the I/O besides disk. Yeah. In the design of the CloudVisor, we only identify the I/O devices into network and disk, and we assume disk should be kept with integrity and privacy. And for the network I/Os, the virtual machine itself should be responsible for all the traffic.
Yeah. So I got that. How about clock? How do you know clock is actually? Don't you need like the clock to be secure? And how do you do secure clock?
Yeah, this is a kind of attack that if the hypervisor tries to manipulate the clock, the timing of the virtual machine, and it probably would cause the misbehavior of the virtual machine in a random way. However, we regard it as some kinds of DOS attack. And as long as the data content in the virtual machine is not compromised, and we would like to assume that it's not our current goal.
So to summarize, you sort of convince yourself that by compromising the clock, you won't lead to data confidentiality compromises. That's sort of, I think, what I heard.
And I guess you can, in a clever way, you can exploit using timing. However, currently it's the bar is rather high, and maybe we could attack that problem if that's become a significant problem.